Hello, I'm Tom Cherryholmes with another video in the Amiga as a Workstation series. In the previous videos, we started our little primer of the Amiga, giving a basic indication of its functionality, and getting our C compiler set up so that we could do some development. We also, once we set up the compiler, did a few compiles of some example applications. And the compile times for these particular applications, to say nothing of the linking times, definitely left a little bit of something to be desired. Well, what can we do about that? Well, we know that we definitely want some more memory than the 512K of memory that we currently have attached to the Amiga 1000. The good thing is that we can add additional memory onto the site expansion. This memory will be dedicated to the 68,000 processor and will not have its cycles stolen by the chip memory, making it fast memory indeed. And in fact, this is exactly what this was called in Amiga terminology, fast RAM. And we can have roughly up to 8.5 megabytes of all of total RAM once you calculate the 512K of chip memory and the 8 megabytes of memory that we could potentially put onto the side. Now, of course, being 1986, we are subject to 1986 economics here, and roughly 1 megabyte of memory with an expansion card would be roughly about $500 per megabyte. So we really have to be careful and not break the bank here. So what we'll do in this particular video is we will take and put a 1 megabyte memory expansion on this Amiga 1000. We will take and do some modifications to the scripts so that it can utilize this memory to speed up compilation. So with that, let's get started. So I went back through and did a recompile of the one window demo here using a stopwatch here as a reference to show exactly how long it takes to do the entire process of both phases of the C compiler and one phase of the linker. And roughly, it splits roughly half and half. So 2.5 minutes for each phase plus another 5 minutes or so for the linker here. And in this case, the big reason for that has to do with the fact that the floppy drive is comparatively very slow. And to let you know what I mean by that, the Amiga floppy drive is controlled by the Paula chip. And the Paula chip has full DMA into chip memory. And it can use the Blitter and the Agnes, and along with the Paula, to very quickly take and read and or write tracks at a time on the disk. What this ultimately means is that given a 3.5-inch disk rotating at 300 revolutions per minute with the standard Amiga file system format with as thin sector gaps as humanly possible because we're reading and writing whole tracks at a time, we basically hit the theoretical maximum transfer speed that is allowable on this drive. And if you take and convert that to kilobytes, that's roughly 22.5 kilobytes per second. And that's for each track. Each track, 22.5K a second, tech, add on some additional pauses, and you can see that, yeah, the floppy disk drive is quite the bottleneck. The way that we're going to solve this in this video is a bit novel in terms of the Amiga, because the Amiga not only allows you to add memory to the system, that memory is then available for programs to run on the system, but also available dynamically to the RAM disk that AmigaDOS provides. So you can store software up there to run very quickly. And that's exactly what we're going to do. But first we need to take and add a memory expansion. At this point in time, there were a handful of hardware manufacturers that were making ready-to-use RAM expansions, But we're going to get our RAM expansion from another source because it gives me an opportunity to introduce something that was very pivotal to Amiga users in the very early days of the Amiga, all the way to the last days of the Amiga. And that is, quite literally, the Fredfish disk collection. From 1985 until roughly about 1998, Fredfish produced over 1,120 individual public domain disks containing a wide variety of software ready to run, source code, and all sorts of hardware plans and everything that we need here. And there's all sorts of stuff that Amiga users got access to. And the earliest disks were quite literally repeats of what had been posted onto Usenet, bringing these things that were previously only available to people who had access to Usenet to a much wider audience. And you can see things like the colorful demo that you may have seen on the Workbench demonstration, on the Workbench demos disk, all sorts of interesting little Hello World applications here on the first disk. Interestingly enough, you'll recognize some names here, such as Robert Pariseau, Bob Pariseau from Amiga Inc., and even the great John Draper, aka Captain Crunch, was also a prolific Amiga user. You'll see bits and pieces of code from people like Dale Luck, another Commodore Amiga alumni, and so on and so on. And these first handful of disks provided all sorts of interesting things that especially early software developers really needed, because all this stuff was being produced on very much a need basis. You had people basically making simple make utilities because Lattice hadn't ported their Lattice make yet. You had better text editors, such as Micro Emacs, which would eventually be posted onto the Workbench Extras disk on 1.2 and above, after it had gone through a bunch of different iterations. But there's all sorts of amazing things, and these tools were absolutely indispensable. That's the last time I'm going to mention about this. Oh, by the way, there's the one window demonstration that we actually put together here that we compiled. But one of the disks that we're going to be looking at here in the very early days here is disk number 27. And the reason that we're looking at disk number 27 is because we have mem expansion here, which contains, among other things, schematics and directions for building your own homebrew 1 megabyte memory expansion, courtesy of Michael Fellinger. So, assuming that we take and build this thing, we get it running here, how is this actually going to work? Some of the eagle-eyed amongst you who are Amiga users might say, well, it's AUTOCONFIG, the memory will just be seen. No, not really. This is before 1.2, so AUTOCONFIG was not a thing. So you had to be very cognizant of where you placed your memory inside your address space, and you had to do all of that manually. You can see here that I've opened up a window here of the Amiga's memory map, and we see the locations of the 512K of chip RAM, the 10R1000 here, and the ECS bits, which are not relevant to our system here. These would come later. But you can see that we have, starting here at address 200,000 hex, the first bit of what can be up to 8 megabytes of fast memory. Seeing as we're putting fast memory in the system, this is where we need to put our 1 megabyte of memory. We'll go here. But we can't just hardwire this in hardware and decode this to that address and we're done with it. The operating system doesn't know anything about it. Right now, if we take and do an Avail, let's do an Avail by basically inserting the Metacomco assembler disk, which we're going to need here in just a moment, actually, the Amiga Macro assembler. We'll go to DF1 and we will go to the C folder here. Okay. And there will be a handful of commands that will be useful here to us. One of them here is Avail, which lets us know exactly how much memory we have available to use. And you'll see from here, we basically only have 395K of memory available, even at this point, after trimming the fat and only just using the CLI interface here. We can go ahead and go in and add our memory expansion, making sure to make sure that it's in our fast RAM slot. And we will add 1 megabyte of that memory here. And you can see the address range where this is actually being set at 200,000 to 2FFFFFF. Okay, great. So now that we've done that, and we basically reset the system here, we're going to notice something here. I'll go ahead and pause so we don't have to actually take and sit through waiting for the Kickstart to restart. Okay, now that I've skipped over all of the boot, we can see that we're back in our environment here. We've inserted our memory expansion, inserted onto the side bus here. And if I go and run Avail again, wait a minute, where's that memory? It's not here. Again, this is before AUTOCONFIG existed. So you needed to tell the operating system that the memory was there and available to be used. It would need to be added to the stack of heaps. To do that, on the macro assembler disk that Commodore provided, Commodore also provided another utility called AddMem and StartAddress. StartAddress has to be run first to indicate where the new RAM will actually start, but we also need to run AddMem, giving the starting and the ending address of our new memory. Once this is done, you can see that we've added 1 megabyte of memory to our available heap, and this time, if we run Avail, we'll see that we have roughly 412K of chip memory available this time. So our chip memory actually increased, but we also have this 1 megabyte of fast memory that's been added to the heap. So we have roughly about 1.5 megabytes of memory now available. And we can have up to 8.5 if you take and factor in both the chip and the fast RAM and you populate the entire address space. So that's possible. We may very well do that at some point in this series. So now that we've done that, we know that we want to take and have this so we don't have to type this in every time. So let's go ahead and let's go ahead and copy the two tools that we know we absolutely want into our commands folder so that we can have them onto our development disk. Once we've done this here, we can then turn around immediately and then go to our scripts folder and add these two commands to our startup sequence so that they happen automatically. Again, the startup sequence is in the S or scripts folder. Again, this is all we have thus far, and that's fine. Now we just, again, just like we did outside, QFF. And that's all we got to do. Now our startup script is set up. And the next time we boot into our environment here, the 1 megabyte of fast RAM will be ready for us to use. Now, of course, the compiler can use this to compile larger bits of software. But I'm going to show you something here. You may not have seen it. In fact, you didn't see it on the workbench here, which is why people get confused by this. But if we look at the assignments, we'll see something very interesting. we see our directories, but we also see in devices, we have DF1 and DF0, our floppy drives, our printer and parallel ports, our serial ports, our raw serial ports here, our raw console and our console devices. But we also have RAM. That's the RAM disk. And for those of you who are saying, well, wait, the RAM disk only showed up in 1.2, only partially right. The workbench would show up on the workbench in 1.2. And in fact, in later fixes of 1.1, this was also the case. But the device is right here. We can use it. If we actually take and do info, we will see that the RAM disk is actually here. And the first time that we access it, TriPOS will realize that we're asking for it and mount it. There we are. So now the RAM disk is sitting here, read-write. We can now take and use it for our purposes. And what we're actually going to do is we're going to make a little modification to our, we're going to make a little script which basically takes and copies our environment into the RAM disk. And this is easy enough. All we really need to do, first of all, let's make sure that we have the correct disks in place. cdevel into drive 1, ccli in drive 0. And we can then take and make a little script in the scripts folder called ram-devel. And the purpose of this script is to copy the so compilers are faster. What do we need to do? Well, it's not much, as it turns out. We need to make directory RAM. We need a place to store the commands. We need a place to store the C libraries here. And that pretty much takes care of most of it right there. Okay. Once we've done that, we can then take and copy the contents of C to RAM C, and we can copy the contents of to RAM lib. After which, we just need to do a couple of strategic assignments. If you do an assign of an existing assignment to a new location, it will take and simply switch to the new location. So this is perfectly fine. We can also assign lib to RAM lib so that the libraries can, so the linker can find the libraries from our make scripts, and we're good there. Save the result. Once that's in place, maybe we also want to take and provide the MakeSimple and some of the other bits and pieces. We can do just that. Let's say, let's copy from the examples folder, make, and copy make, etc., all those, and we're going to throw those into the commands folder. We might want to use them, at least for now, until we get better tools. So there's make, which just runs the C compiler, MakeSimple, which runs the compiler and the linker. We go ahead and copy the link script over as well. And really, we just need to make a small little adjustment to each one of these. We want to take and edit CMake here. Make sure that we don't have any ill-placed paths. Actually, this looks just fine. We'll go ahead and make Oop, make sure we have the right file name here. Q abandoned. MakeSimple. Okay. You can see right here that we have an assignment statement right here, which will take and obliterate our lib statement. Yeah. Okay, fine. We can either we can either override the assignment, or we can just make the modifications here. 6 of one, half dozen of the other. Let's see if the same thing is here. Actually, it looks like they don't try to do it here in the link script. Oh, they do. Okay. Good thing I did this. Bang. There we go. We save the results. We have them in the scripts here. And now we have everything modified. And we have our little script that we know that we've run here. And we can do a dry run here to see how this is going to run here. Just execute it. Oh, execute. And this will take a few minutes to take and copy the commands to the RAM drive, all of the compiler commands, the libraries, and all the bits and pieces so that the C compiler can do its job. And in point of fact, actually, I realized too, we really want the includes here as well. So let's go ahead and fix that. So I will actually take and fix this here by basically taking this and copying cdevel to RAM and do all. Sure, this will get everything in place and handle all of that. So now we go again. And this will take a few moments to take and copy everything over. You'll see that we've now moved over from the CLI disk to the cdevel disk because we're now copying the libraries and then now the include directories as well. You might be wondering why there are what are called FD files that are present on the Lattice C disk. And that's rather actually kind of interesting because it essentially allows certain language environments like Amiga Basic to be able to access external functions that are defined in these files. It's essentially just it's essentially what they're called function description files. Amiga Basic can use those FD files and to specify external functions, which you can then take and point to from libraries that are loaded off of the disk, and therefore allowed you to take and write basically functions that you could take and then call from languages like Amiga Basic. Okay, we're here at the bottom of this. We should be good to go. Almost. Okay, so after examples is done here, we should be good to go. So now we're back to where we were. Took a few minutes, but now everything's copied to the RAM disk. And if we look at our assignments, you'll see that lib now points to RAM. The commands now point to RAM. Libs is still pointing onto the floppy disk, and that's fine. It really doesn't take a performance hit here. Same with scripts, etc. But if you want to make other additional assignments, you can take and put them into that file. There you go. To each their own. But now that we've done this, let's go to RAM examples here, and you can see that we've got our examples folder sitting on examples. So you can have on top of your development tools, you can also have your source code sitting here in the RAM disk as well. So everything stays here and you don't hit the floppy drive. How does this look from a file system perspective? Well, we are using roughly 932K worth of our RAM right here for our RAM drive. We still have, you'll notice that currently, oh sorry, I'll finish that sentence in just a moment. You'll notice that at all times, the way that the RAM disk actually works, it's always at 100%. This means that the RAM disk dynamically expands to allow whatever files to be copied to fit inside of it, contingent on the amount of RAM that you have available. I mean, let's see if I still have. Did I not oh, I never copied the Avail tool into my system here. That's no problem. I can do that real quick. We really don't need this disk anymore, so I can take and get rid of that and throw the macro assembler back in here. And I will copy from DF1C Avail, and I will move that over to C so that it can be copied the next time. Sure. And I'll make a copy of it here. Avail DF0C. Because I already did the assignment. And now that we've done that, I can take that now and I will go back to the RAM disk here. Sorry. We will remove that disk that I dropped in here. We still have the CCLI in the main in the main system drive here. If I run Avail at this point, you'll see that we're kind of back at the same situation. We have roughly the same amount of RAM that we had available before we started the RAM expansion here. But we're starting from a point of view that everything is running out of RAM now. Kind of cool, huh? So what does this mean quantitatively? Well, we can go back to our examples folder. And we can boot, and we can, let me make sure that did I change you? Oh, let me edit you. Copy. I'm just going to remove MakeSimple because I already have a copy of it ready to go. Oh, wait, it can't. Okay, sorry. Execute C, MakeSimple. One window. Just like we did at the top of here, where you see I've kept the time that was clocked here at 9 minutes and 19 seconds. We're going to take and run the compiler now with everything in the RAM disk. And we're going to see how long it takes for the process to complete. Compiling one window C. And you'll notice that the floppy disks are not being accessed at all. Everything is running out of RAM. We have now gone to phase 2 in just under a minute and 10 seconds. We've entered the linker at 1 minute and 22 seconds, 1 minute and 20 seconds. And even here on the RAM disk, you'll see very quickly why the original A-Link was replaced so quickly by B-Link. A-Link was extremely slow, even with all the bottlenecks, even with all the I/O bottlenecks removed. There we go. Linking complete. We've now finished the whole process at just under 2 minutes and 50 seconds. Recall before it was 9 minutes and 19.6 seconds, so 9 minutes and 20 seconds, down to 2 minutes and 52 seconds. So we're literally seeing it take even better than 1/3 of the time that it previously took by moving everything out to RAM. So I'm going to go ahead and end the video here, but I wanted to take and demonstrate this to show you some of the things, one of the things that we did as developers, which was quite literally to take and use the RAM disk to put as much RAM as we possibly could in the system and to leverage the RAM disk as a very fast disk store for running our compiling, our development tools and working on our code. It turns out it cleared out the disk bottleneck quite nicely. we'll see where to go in the next video here, but I hope you all enjoyed this, and until next time, guys, have fun.